Hello, my name is Aristuro, and this is my Earth Space Science Art slideshow. This is the moon. The moon is Earth's only proper natural satellite. It is the largest natural satellite in the solar system relative to the size of its planet and the fifth largest satellite in the solar system. I use gray marker and watercolor.
Are we seeing Iris's art?
And we're not seeing her art.
I'm happy to share the slideshow while Iris reads, if that would work, if you could let me do that.
Yeah, all you have to do is, yeah, there you go.
You guys aren't seeing her slideshow?
We were not, no.
Oh, okay. That was a good practice, I guess. Take
Looks
two.
like, yeah, Monica's got you covered.
Thank you, Monica.
I got you. We're a good team.
Thank you, thank you. Okay, I guess you get to do take two, Iris.
Yeah.
You're doing great, Iris. Can you see it now?
Yep,
Awesome.
looks good.
Hello.
Well, you've introduced yourself, so you have to go to this page. There we go. This is the moon. Go.
Oh, this is the moon. The moon is Earth's only proper natural satellite. It is the largest natural satellite in the solar system relative to the size of its planet and the fifth largest satellite in the solar system. I use gray marker and watercolor. This is the Milky Way. The Milky Way is the galaxy that contains our solar system from Earth. We can see a hazy band of light seen in the night sky formed by stars. I use markers and watercolor. This is the aurora borealis, beautiful northern lights, and aurora, sometimes called polar lights, northern lights, or southern lights, is a natural light display in the Earth sky seen in high latitude regions. Auroras are caused by solar wind. I use dual pen for northern lights. This is a comet. A comet is an active small solar system body that, when passing close to the sun, warms and begins to release gas. A process that is called outgassing. This produces a visible atmosphere or coma and sometimes also a tail. I use watercolor and markers. This is a gas giant solar system. Jupiter, Saturn, Uranus, and Neptune. I chose this because I like galaxy background. I use my new watercolor palette. Thank you for watching my presentation.
Thank you, Iris.
Yeah, thank you very much. That was very nice.
Thank you.
We really love your art too. That's great. We're so glad you could join us tonight.
Good night.
So now we have our monthly sky report from Jim Todd. Take it away, Jim.
Well, hello, everybody, and hope everybody's doing well. And I'm going to go right through this real quickly for the month of May. We have a lot of things happening in the month of May alone. So let me get right to it, Ashley. Start with the beginning of the slide, not at the end. How about that? Okay, so it's my turn, Margaret.
I'm done.
Yeah, and getting the issues through here.
Are you having trouble sharing, Jim?
No, no.
Okay, there you go.
It's
Okay.
it's called human error.
Oh. We never do that.
So that was a great presentation. That really was. Okay, so here we go. Since the last meeting, we had quite a few events that happened, and we have, of course, the next full moon going to be on May 26th. It'll be a little special. And March 2020 continue to put on a great show. On April 21st, it was able to convert the make oxygen using MOXIE, which is quite an important step for being able to go to Mars and providing fuel, because Mars has 98% carbon dioxide atmosphere, 100 times thinner than the Earth. And so they put the MOXIE, soon after they did Ingenuity, they did MOXIE, and it was able to produce oxygen quite well. And so one of the things in Martian, the oxygenator and the water reclaimer is critical if we're going to go to Mars. So here's an example right here. If you play with oxygen, boom. Okay. Well, it could be very challenging. So that's a part of the motion, is to try to find a way to produce oxygen. And that was one of my favorite scenes. Okay. And then we had the crew launch on the 23rd, crew 2. A very successful launch. This time we had a crew of 4, and really diverse now as far as the crew goes, and it's got out to 11. And so it was very challenging to find sleeping quarters on the International Space Station. The fact is, the most they ever had was 13. They were just close, but they had to make accommodations. Some slept in the Dragon, some slept in all parts of the station. And so Ingenuity had a microphone turned on, and you can actually hear it, the very low hum. And so with this low hum, you can hear Ingenuity come and go. This is a sound from another planet. How cool is that, right? And so Ingenuity, it had an extended mission. It was supposed to be only for 1 month, but it got an extended mission that it's going to kind of go along with Perseverance and do some support. But the Mars 2020 crew said, Ingenuity, you're on your own. We got lots of other work to do. Right? Then Michael Collum passed away, the second Apollo astronaut that had been passing. And so Michael Collum was well known for to be the one that's in a command capsule while the 2 were down on the surface of the moon. And he made a comment that he was the loneliest man in the universe to be outside of that capsule where the moonwalk was occurring. And then the crew 2 had a successful splash landing, which was the first time it was a night landing since the early Apollo. Right? So that was very successful. What's interesting though, they got quite seasick, sitting there waiting for get off of the Dragon. They got a little bit seasick while they were waiting. And then we had the May 4th event. And then we have a very bright nova. And it's visible now, well, sort of, but it's been visible. And some of you may have seen it. It's actually a kind of a convenient location, just right next to M52 in the Messier object, or the Bubble Nebula. And I personally have never seen the Bubble Nebula. I've seen M52, but I've not seen the Bubble Nebula. And so the nova occurred, and it got really bright. And this is kind of the location for Nova Cassiopeia 2021. It's actually pretty interesting. And then what happened though is that it was dim for a while, then it got really bright. Got up to about as you can see, almost to the 5th magnitude. And then it's now dropping again. Okay. So what's happening here? So we have a nova occurring where we have a white dwarf next to a very bright star, and then it had kind of a what I call a Star Wars event where there's nova that's occurring. Okay? And then, if you haven't noticed, finally the Chinese rocket came down. There was a lot of speculation to when it was going to come down. This is part of the booster rocket that put the Chinese space station in orbit. And the stage 2 was supposed to be deorbiting, but it was an uncontrolled deorbit. And everybody got kind of like a betting pool that was going on. That was where it's going to happen. And so I don't think there's audio on this, but the reporter asked the United States, they plan to shoot it down. Hello. So I was amazed that even that reporter had that question. And it came over the island of Maldives, just kind of south of Sri Lanka. And it came down in that area. And one other side said that's exactly where it was going to come down. And they were right. Right? But no parts have been found. Nothing came out of it, except it came close to the island. I don't know if there's any habitat there. But this is one of those that this object was about 10 tons. 10 tons. It was the largest debris that entered back to Earth since the Skylab. And so you would think something would have come down, but apparently it all burned up. China was not really worried about it, that the odds were very small, all of that. But you know, it was an event, and I was actually glad it was over, so we wouldn't have to guess when it was going to come down. Right. The sunspots are not really, they're pretty active right now. So the sun is definitely showing some signs of activities. We see the early stages of cycle 25. Almost a few days ago, it really spiked. And unfortunately for Oregon, it didn't quite have that energy, but there were plenty of auroras up in Sweden and Finland and Russia. They had a great show up there because it was really intense. This is the ovation for today. Not really any chance the KP level remained down, but we are due to one for the next maybe another month or two, but for the next few years, we will get our turn. And then China was successful landing their rover on the surface of Mars. And you can see very similar technique to the Perseverance, March 2020, in many ways. But China was orbiting Mars for a good number of days before they decided where to land the rover on the surface of Mars. So this was a big achievement for China because this is the first time they've ever landed anything on the surface of Mars. And so they had a very successful landing. They may roll out the rover sometime this weekend, right? And then hopefully you got to see this great display this past week of Venus, Mercury, the Moon, and Mars. It was a great show all the way across. Venus is particularly bright. Mercury is dim, but you can still see it. It was pretty easy to find. Mercury is kind of in the middle between Mars and Venus, and Mars is still quite visible, and it was literally touching each other with the waxing crescent moon. It's still visible. But for the next few days, Venus is going to continue to get higher. Mercury is going to start going down. And by the first week of June, it'll be below the horizon. But Venus will be very prominent in the evening sky. And I'm going to try to rush through this. We have interesting with that Starlink you were talking about. We have just a 24Y had a carrier, and this particular CubeSat actually had a space telescope, had a little telescope on it that I found out today. And so maybe we'll get some pictures out of it. Okay. And then just recently, just not too long ago, they had a launch from Wallop, which is to talk about the energy transfer. Electron launch failed. And looking ahead, the planets pretty much Mercury, as I show you, Mercury, Venus, and Mars, and so on in the evening. Jupiter and Saturn starting to be in the morning. Object will be Messier 101, Pinwheel Galaxy. Really nice object. And the Big Dipper being overhead, this is a great time to look at 101. And the space station will be visible through June 1st. And try the China space station. It's actually visible, but it's much dimmer than the space station. And then we have full moon on the 26th with the super moon, flower moon, milk moon. Then we have a total lunar eclipse on May 26th, 4:18 a.m. And so we have an opportunity to see it, but it's going to be darn low. Only 14.5 minutes long from 4:11 to 4:25, 10 degrees above the horizon. And we have the star Antares nearby, which have made some for interesting viewing. If we don't get to see this one, you can see it live stream on date and time, which will be streaming. And then follow that on June 10th, we have the annular eclipse. Nothing for us, but that 14 days later. And so it'll be over Europe and various parts, mainly in the north. You can also watch that on date and stream, date and time as well. Okay. And we have a bright comet, and that's going to be 11th magnitude, and it's going to be around May 27th and June 12th. Okay. And then the missing Milky Way, which is going all the way around the horizon now before midnight. And so people always ask, where's the Milky Way, Jim? And so that's what's happening, is that it's going to be parallel to the horizon. And people can't find it. Well, that's what's happening here. And then that's a great opportunity to look at the Virgo cluster overhead. And you look at the diamond of Virgo, where you can see 1,000 of galaxies. Some very faint, some are very bright. But this is a great opportunity to look at the Virgo cluster. And so the next full moon will be on June 5th. And then we have the summer solstice on June 20th. Coming up, and that's going to be the meeting date, actually, for the month of June. Plenty of things to get a picture of. And with that, stay healthy, and that's the report for May. We'll see you in June.
Thanks a lot, Jim. That was great as always. We'll now be moving into our separate sessions. So if you're the host for a session, please leave this meeting and start your meeting now. And then for anyone who wants to enter another session, you just leave this meeting and then you click on the link in the email message that corresponds to whichever other session you wanted to participate in. The one other thing that I probably should mention is that we will not be having the dark sky preservation session tonight. Dawn Nilsson had a death in the family and she could not be with us this evening. So apologies for that. We wish the best for Dawn. And
Mark, I could do a Mars program in place.
Well, the tricky part, yeah, it's just too tricky to organize on the fly, Jim. Yeah, thanks though.
Totally understand. I'm just an offer.
Yeah. Okay, thank you, Jim.
Hey, Mark. Mark,
Yes?
this is Jeff Lee. I'm trying to get
Yep.
into the observing session
Yep.
and it's not happening. It just keeps spinning. It says
Okay.
it will start shortly.
It could, well, then, yeah, you just need to wait. So you'll need to leave this meeting because you can't be in
Yeah.
two meetings at the same time.
Right.
And then click on that meeting, and it's just configured so that the host has to be there before
Okay,
before you can enter.
okay. Gotcha. I'll try it. Thanks.
All right, sure. Okay, so for those of you who are still here, this is going to be the cosmology astrophysics session. And our first speaker is going to be Victor's Burstis. Victor's is, he was an IBM senior software engineer and master inventor. He was also the lead scientist for the World Community Grid. And he is the coordinator of our cosmology and astrophysics special interest group. So please welcome Victor's Burstis.
Greetings.
And thank you, Victor's.
Can everybody hear me?
We got you.
Okay, I'm going to play a recording of my talk. So I'm going to share my screen here. And then we'll have some time for questions afterwards. Hi, I'm going to talk about a theory of how our universe came to exist. If you're like me, you've not heard of any satisfying explanation elsewhere. Even Stephen Hawking's book, The Grand Design, fails to really explain why there is a universe like ours. He talks about a quantum event creating the universe from nothing, but what is the setting that allowed that to happen? And what created that setting? Is there something that exists that does not need creating, that can create a universe? And what is it? And we have other questions. Why is the universe exactly as it is? Of all the imaginable, infinite possibilities, why is my pencil over here instead of over there? The probability of being in exactly this kind of universe is 0, given that there might be an infinite number of them. Or why didn't the Big Bang, maybe starting from a single mathematical point, explode into an exactly symmetrical universe? I hope to answer these questions for you. There are several pieces we have to put together to form the big picture. First, let's talk about computer simulations. You've probably seen some realistic video games like SimCity, SimFarm, and many others as examples. To make them more realistic, these games calculate how objects should move and appear based on real physics equations, some kinds of rules, basically. And using these equations, they produce results which are quite compelling. Scientists do this too when they are working in biology, chemistry, electronics, weather prediction, and many other fields. They apply the best scientific formulas to try to approximate what nature seems to do, but do it rather inside of a computer instead of in a laboratory or in real life, so they don't have to spend a lot of time and money doing it for real. This lets them predict, for example, how a potential chemical may or may not be able to help cure a disease, or whether a design of a bridge is likely to survive an earthquake, or whether a new airplane design will fly. Some of these simulations are rather precise, but they are not exact. This is because they don't consider everything that nature has to throw at them. To make a truly exact simulation, they would have to simulate the behavior of every atom, actually every particle that is in any way involved. And where would you stop? There are almost 10 to the 28th power atoms in just one person. But to really get things right, you have to simulate all the atoms in the air, the land, the water around you, and so forth. To simulate the ocean tides, you have to include the atoms of the moon and the sun. And to get the sun's energy included, you have to simulate the photons too. And you have to include all the meteors and asteroids that may or may not hit the Earth, not to mention a lot of other stuff. And even then, the simulation would not be quite perfect, because even other stars and galaxies have some effects on Earth, even though they're usually very, very small. And occasionally cosmic rays from extremely far away can come in and hit some DNA molecule and mutate it to give you cancer, for example. So to simulate everything exactly, you would have to include almost the whole universe in your simulation. And quantum mechanics makes it even harder. But I'll explain how to handle that later. So the real problem is that the computer you need to get an accurate simulation of everything in the universe would obviously have to be much bigger than the universe, making it completely impossible for us to simulate anything exactly in practice. But let's just for the moment think about someone in some sort of other universe who does have a computer much larger than our universe that can simulate our universe exactly. It would be like a Sim Universe video game to them. It would be quite a bit more elaborate than our old Sim City game, to say the least. They could watch the stars, the planets and galaxies form and life evolve here and there. Yet for them, it is just a computer program running on their big computer. The next big point I want to make is that all computer programs can be rewritten as equations in mathematics. These equations are called Diophantine equations, but I'm not going to go into the details of those either. The real point is that in theory, there is an equation somewhere in all of mathematics that represents an exact simulation of everything in our universe. Obviously, this equation might be hard or large for a human to comprehend, but it is there. Now let's jump to another important point. What is mathematics? Some people think that mathematics is a human invention. It is not. Only the notation and names we use for mathematical concepts are human inventions. Having studied a lot of mathematics myself, I realize that mathematics exists whether there are any humans or not, whether there is any universe or not. The notation we use and the names we use to talk about things in mathematics are human inventions, but the underlying mathematical concepts have always been there, ready to be discovered by anyone with sufficient intelligence. Any intelligent species that happens to come along and learns how to count and measure things will soon discover arithmetic, invent a notation for writing numbers like Roman numerals or our popular base 10 system, and the many other ways of writing numbers and mathematical statements. They will discover that if you assume certain rules that mathematicians call axioms in logical operations, you can discover that those axioms lead to a rich world of mathematical concepts. What is interesting here is that mathematics exists without being created in any way. Anyone coming along and discovering counting and arithmetic, for example, will at some point discover the concept of prime numbers, and that 7 is a prime number no matter what it is called in their language. If nobody ever came along and did not discover counting, arithmetic, etc., they would not discover that 7 is a prime number. But even if nobody discovered it, nothing can change the fact that 7 is a prime number. So, can we pin the existence of the universe on mathematics? Something that exists without needing to be created? The answer, I think, is yes. In our universe, it may not be a coincidence that particles and forces obey very specific rules, which can be precisely described using mathematics. So what I am really saying is that our whole universe is simply an equation somewhere in all of mathematics. It does not matter that we have not yet discovered what that equation is exactly, but it is there somewhere. Remember, mathematics is infinite. There is an infinite variety of possible equations, infinite interesting things of all kinds. We simple humans can never hope to understand everything that mathematics contains. If our universe is an equation, you could say that every equation in mathematics describes a universe. This would imply that there are an infinite number of universes. In fact, every possible universe has a description in some equation somewhere in all of mathematics. Let's take the equations that make a point move in a circle. That is a universe, but a rather boring one compared to ours. In fact, most equations make for boring universes. To get interesting universes, you have to have equations of at least a certain size, which happens to be around 68 bits of information, giving your equation the power to compute anything by a concept called a universal Turing machine. I don't want to dive into the details of universal Turing machines here either. But you do need an equation complex enough to describe an interesting universe like ours that can evolve intelligent life. I might add that even rather simple equations can actually create infinitely complex results, as in the Mandelbrot set, for example. But you probably are thinking an equation is a static thing. It does not move atoms, it only describes their motion. And here is where I add the big missing idea. Yes, when we look at some equation to see what the universe it describes looks like, we have to do some work, like put it in a computer and let it play out by simulating what happens. We are observing that universe from the outside in this case and looking into it. We are not part of that universe. We are observing from the outside and thus need to render it on a computer to see what happens. But when you, an intelligent being, is part of the universe, you're observing the universe from the inside, and that is very, very different. Everything seems real, and things behave in that universe according to the equations that describe it. Think about SimCity game or a more advanced Sim Universe computer game. Let's say there are intelligent life forms being simulated in that Sim Universe game. They think everything in their reality is real. The equations don't let them walk through walls. They perceive other objects and things happening in their universe while the computer game is running. If you pause the computer and then start it up again, they will not know that it paused. Everything that happens in their universe is determined by the equation, not by how your computer works. Their time is not really moving time like we intuitively think of it either, but rather it is a causality structure that comes from the equation. The equation determines the entire history and future and the causes and effects of everything in that universe, whether that universe is simulated or not. You just need the computer or some other rendering method to be able to see what happens in a universe when viewing it from the outside. You don't need a computer to see what happens when you are viewing the universe from the inside. It depends on your perspective. You could call this the theory of perspectivity. In a way, I am saying that time does not exist the way you feel it. It is more like what time is in a movie or a DVD. There is a big equation for the DVD consisting of a few billion bits of information that describes the movie. It takes more bits to describe a scripted universe like a movie because it is not based on a simpler set of physics rules. When you play it on a DVD player or not, that movie's path through time is predetermined. We call that being deterministic. And when people hear that everything is deterministic, they argue that free will is a counterexample. However, you have to think about what the term free will really means when you use it. I think it means that to some extent, you and your brain are not constrained by external factors in making choices about what to do next. You are, however, very constrained by your own self and your brain. That is, your choices are predetermined by the laws of physics, chemistry, and biology going on in your brain. Your brain comes up with a decision based on your memories and whatever other senses or inputs you have. If you could put yourself in exactly the same state a second time, exactly the same memories, inputs, environment, you would choose to do exactly the same thing. You cannot, of course, do this because you cannot totally reset your memory and environment to the prior state. However, Alzheimer's patients unable to make new memories come close to doing that, and that is why you often see them doing the same thing over and over again. If your brain is not making the decision, then your decisions are either random or subject to some external entity making your decisions for you, and even that entity's decisions are predetermined by the laws of physics. Some may say that quantum events could introduce randomness that might make your decisions slightly undeterministic. The best answer to that goes back to Hugh Everett's interpretation of quantum mechanics, which is now being more and more accepted. It basically says that every quantum event splits the universe into multiple copies, which include all the possible random outcomes of every quantum event. This solves the mystery of quantum weirdness or spooky action at a distance, as Einstein called it. It makes it totally logical. Your body is also copied in the universe splitting process, and when you do the quantum experiment, you discover which copy of the universe you're in. Schrodinger's cat is alive in one copy and dead in the other copy of the universe. And there are copies of you in those two branches of the universe. And how does one simulate this quantum randomness? You simply simulate all of the possible outcomes of each quantum event. Picture a copying action which copies the universe into multiple versions according to the possible outcomes of a quantum event. The copying moves outward from the point of the event at the speed of light. Each copy can no longer communicate with any other copy. When two outward copying actions intersect, they get a multiplying effect, so you get at least 4 copies and so forth. It makes the simulation look like cauliflower in a way, but much more branchy. But in mathematics, very large things or even infinite things are not prohibited. It just bothers our limited intuition. Max Tegmark recently wrote a book called Our Mathematical Universe, which agrees with most of what I'm saying here. However, we do disagree on some fine points. For example, he claims the theory is testable. I say that it is not. A theory that explains how every universe exists cannot be tested because there cannot be a counterexample universe to test it with. And that is why this is covered by philosophy more than science. Most of the ideas here have been around for a long time. See the Moriarty episodes in Star Trek. They will make you think more about simulations of a universe and how perspective matters. Hugh Everett came up with his interpretation of quantum mechanics back in the 1950s. The deterministic universe idea has been around for a very long time and has suffered all kinds of bifurcations from religious and moral arguments and taken many twists and turns. Straightening all that out would require a whole separate lecture or more. The famous mathematician Gauss once said, "Mathematics is the queen of science." I think the perspectivity idea was the last thing missing in a logical explanation of how the universe exists. It makes mathematics the mother of the universe. So what does it all really mean? Mathematics exists without being created. Every equation and its solution in mathematics can be thought of as a universe. And there are an infinite number of universes. Only the one that we are in seems real to us because we are viewing it from within. Going back to a couple of original questions I mentioned, why is my pencil over here rather than over there? Well, it could be over there in a different universe that has an additional physics rule to put it there, an exception to the normal rules, you might say. A rules-based equation for a universe can be rather compact, but maybe the universe is scripted. There might be a script for how every particle should move through time. This would need to be an incredibly larger equation. Well, any equation can be rewritten in many different ways and yet describe the very same thing or the same universe. Shorter equations statistically would have more equivalent equations, and thus shorter equation universes are more probable than long equation universes. We are probabilistically more likely to be in a shorter equation, rule-based universe rather than a much longer equation, scripted kind of universe. Why is the universe not symmetrical? Actually, one branch of the universe split by quantum mechanics is symmetrical. But again, there are so many branches that the probability of us being in the symmetrical one is essentially 0. Finally, I cannot say for certain that all this explains the existence of our universe, but I don't know of any other explanation that doesn't have some logical holes. You can read much more all about this in my paper on the subject. See 101iq.com/universe.pdf, all in lowercase. All of this might make some people think that we are worthless or purposeless in the big picture of the universe. But that may be, but I would say instead, look at the smaller picture. Enjoy this life and help those near you enjoy it as well, because you are not worthless to those near you. The authors of the U.S. Constitution probably already understood all this because they wanted people to be able to pursue happiness. I hope I've at least provoked you into thinking more about the nature of our existence. Thank you for your time.
Thanks, Victor. So now we have some time for questions. If anybody would like to ask Victor's about things.
No questions? Probably went through all this pretty fast. Later on, I'll probably post it on my site where I keep the cosmology news if you're interested in re-listening. Bob, if you're talking, you have to unmute.
I think Bob is actually juggling 2 different sessions at the same
Oh.
time. So
It looked like he was waving his hand, so.
yeah. So if anyone does have questions, feel free to unmute yourself, or you can type it into the chat, whichever you like.
So is everybody confused or anything? No comments from anybody. All right, well, I guess you can go on with their next part, Mark.
Okay. Well, thank you, Victors. That was very nice. So for my part of things, I thought it would be fun to just talk about some interesting ideas that have recently come to light. Let me go ahead and share my slides here. And this is going to be kind of a hodgepodge. It's just a bunch of things that I thought were kind of interesting. Some of them might not seem as connected to cosmology or astrophysics as you might like, but I think you'll find them interesting. So the first thing that I ran across recently is that we now have a full spectrum image of the M87 central black hole. It turns out that at the same time that they were making the observations of this black hole using the Event Horizon Telescope, they were also observing the same object using all sorts of instruments that span the whole electromagnetic spectrum. So they were using radio telescopes, they were using the Hubble Space Telescope to get the visible and near infrared pictures. They were using the Swift Observatory to get the UV, and also the Chandra and NuSTAR instruments to get X-rays, and Hess, Magic, Veritas, and Fermi to get the gamma ray pictures. And so if you take information from all those different wavelengths and you superimpose them, then what you end up with is the picture that I'm showing you right now. One thing to note too is that all these different instruments actually have different resolutions and they image on different spatial scales. So here's a picture that shows all of the individual images that went into that composite image, and they're superimposed on the electromagnetic spectrum. So here's the spectrum down here, and then there's a list of the instruments that were used to image the different parts of the spectrum. And one of the really cool things they did with this is they put all of these together into a video that basically shows that central black hole for M87 at different spatial scales, and it starts from the biggest spatial scale and zooms in. So I want to go ahead and play that. Oh, and I want to go ahead and play that for you. So I got to let a couple more people in, juggling lots of things here at the same time. So let me switch to the video. Oops. Okay, Zoom is not cooperating. Here we go. All right. Okay, oh, here we go. All right, here we go. All right, let me switch the video window. So this, as I said, this image is going to show all these different wavelengths, but they're on different spatial scales. So you end up actually zooming in to the central black hole. So here we go.
In April 2019, scientists released the first image of a black hole in the galaxy M87 using the Event Horizon Telescope.
Actually, the zooming is going the
EHT.
other way. We're starting at the
Now, data from 19 observatories, both on the ground
black
and
hole
in
and zooming
space,
out.
are being released that promise to give unparalleled insight into this supermassive black hole and the system it powers. These new observations could also help improve tests of Einstein's general theory of relativity.
So those are the gamma ray images, which are the largest
The-
spatial scale.
The immense gravitational pull of a supermassive black hole can power jets of particles that travel at almost the speed of light across vast distances. M87's jets produce light spanning the entire electromagnetic spectrum, from radio waves to visible light to gamma rays. This pattern is different for each black hole. Identifying this pattern gives crucial insight into a black hole's properties, but this is a challenge because the pattern changes with time. Scientists compensated for this variability by coordinating observations with many of the world's most powerful telescopes, collecting light from across the spectrum. This is the largest simultaneous observing campaign ever undertaken on a supermassive black hole with jets. NASA used several of its space-based telescopes in this observing campaign, including the Chandra X-ray Observatory, Hubble Space Telescope, Neil Gehrels Swift Observatory, the New Star Satellite, and the Fermi Gamma Ray Space Telescope. Beginning with the EHT's now iconic image of M87, a new video takes viewers on a journey through the data from each telescope. The video shows data across many factors of 10 in scale, both of wavelengths of light and physical size. Each telescope delivers different information about the behavior and impact of the 6.5 billion solar mass black hole at the center of M87, which is located about 55 million light-years from Earth. The data were collected by a team of 760 scientists and engineers from nearly 200 institutions and 32 countries or regions, using observatories funded by agencies and institutions around the globe. The observations were concentrated from the end of March to the middle of April 2017. The combination of data from these telescopes and current and future EHT observations will allow scientists to conduct important lines of investigation into some of astrophysics' most significant and challenging fields of study.
So there you have it. It's pretty interesting set of observations. Let me go ahead and go back to my slides. All righty. So I've put links to all of the articles and to the videos and so forth in my notes. And my plan is to share those through the website, through the club website when we post all the materials from the fair. So another kind of cool little tidbit that came up was that we now have a new map of more than 25,000 supermassive black holes. This map was made with the LOFAR radio telescope network, and that consists of about 20,000 antennas that are arranged across Europe, and it covers a really low frequency range for radio observations. So in this picture right here, each white dot is a supermassive black hole. And currently their data only covers about 4% of the northern hemisphere night sky, but they're eventually going to increase their coverage and their resolution. Oh, and just for comparison too, they have a little image that shows the size of the full moon. So this is about half a degree across right here. And again, my notes, my slides have the references in case you want to check them out yourself. Another interesting result that came up in the past couple months is that some scientists identified some potential antimatter stars in the vicinity of our solar system. So why is this interesting? Well, the laws of physics suggest that the Big Bang should have created pretty much equal amounts of matter and antimatter, but we don't know where the antimatter went. We only seem to observe matter for the most part, and nobody knows exactly why. But these astronomers went and they took a close look at data from the Fermi Gamma Ray Space Telescope, and they found 14 point-like sources that have spectra that look like, these are gamma ray spectra, of course, that look like baryon, antibaryon annihilation, like you would see from collisions between matter and antimatter. So they suggested that this might mean that there are 14 stars comprised primarily of antimatter within a couple hundred light years of the solar system. And in particular, they estimated that there could be as many as 2.5 anti-stars per million normal stars. So what this picture shows, this disk in the middle is the Milky Way, and this just shows the positions of those 14 point-like sources in our galaxy. And again, here are the references for you in case you want to read it about it yourself. Now I'm going to switch to a slightly different topic. Most of what I talked about so far is astrophysical or cosmological, but I know that there are a lot of people out there that are also interested in kind of unusual concepts of propulsion. And one thing in particular that I've had members ask for in the past was for me to recruit a speaker to talk to us about the EM drive. The EM drive, which is also called the radio frequency resonant cavity thruster, is a device that seemed to violate the laws of physics. Basically, you'd put some radiation into this resonant cavity, and the idea was that you'd have a small force on the narrow end of this conical cavity and a larger force on the larger end of the conical cavity. And this would produce a net thrust away from the larger end of the cavity. And this would violate the law of conservation of momentum. So several different groups around the world have been studying this for quite a while. And the initial results seem to indicate that you could generate about 1 millinewton of force using a fairly small cavity. But it turns out that if you work very, very hard to control all of the environmental factors, that this actually doesn't work. It appears that the very small forces that were being measured in the past were due to electromagnetic effects from the environment of the experiment. So unfortunately, we don't have our magic perpetual motion device. And I guess that's another example of the no free lunch theorem. So there are a bunch of references here about that. And there are also some nice YouTube videos that describe the situation that you can check out. Along similar lines, it turns out that there was some progress made in terms of designing actual warp drives. So what is a warp drive? Well, it's a mode of propulsion that allows you to go faster than the speed of light, basically by creating a wave in space-time. And even though relativity prohibits you from traveling faster than the speed of light, if you're starting from a speed slower than the speed of light, it turns out that that restriction doesn't apply to space-time itself. So if you can create a wave that's moving faster than the speed of light, then you can ride that wave, and that's the idea of a warp drive. Okay, so here I've written down Einstein's field equations, and it doesn't matter, exactly what they mean. Generally, this one equation represents 10 independent equations that describe how the geometry of space-time is related to the distribution of mass and energy in the vicinity. And all that I really wanted to point out here is that the left-hand side, this big G, represents the curvature of space-time. And the right-hand side is called the energy momentum tensor, and it represents the corresponding distribution of mass and energy. And those two things have to be related by this equation to be a valid solution to Einstein's field equations. So there is an example of a warp drive concept that's been around for quite a while, probably about 20 years. And that's the Alcubierre drive. And I'm showing a picture here that shows the kind of distortion in space-time that drive corresponds to. So what Alcubierre did is he came up with a space-time geometry that has these desirable characteristics. But it turns out you also have to deal with the other side of the equation. You have to deal with the stress energy tensor, T. Turns out that if you figure out what kind of distribution of mass energy that you have to create this space-time geometry, it requires some kind of exotic matter or negative energy. And we don't know whether those things exist. So this is probably not a realistic path to a warp drive. However, a paper published in just a few months ago came up with a space-time geometry that acts like a warp drive. So it describes a geometry, the big G, that has this property of creating this superluminal wave in space-time, but it corresponds to an actually physically realizable distribution of mass and energy. So it doesn't require any of this exotic matter or any negative energies or anything like that. However, even though the mass energy distribution has some of those desirable properties, you still have to have an extremely large amount of energy to create this geometry. So much so that this is probably completely impractical. But it's still kind of an interesting theoretical, little theoretical tidbit. And you can read about it in the author's paper. I'm giving you a link here. Okay, another topic that's kind of been in the news a little bit lately is the idea of dark matter and its potential relationship to some new physics. So far, the efforts to detect dark matter in the form of some elusive particle haven't succeeded. And one of the hopes in building the Large Hadron Collider was that it might detect some kind of new particle that could be a component of the dark matter. But the Large Hadron Collider hasn't seen any new particles yet either. It detected the Higgs boson, but the Higgs boson is part of the standard model of particle physics. And so that was something that was expected. And they were also hoping to see a bunch of these particles, which are supersymmetric pairs of known particles, but none of those were found. There might be a little bit of evidence for another potential candidate particle called an axion, but that's still tentative and not very substantial. However, if the standard model of particle physics is wrong, then there might be some dark matter particle candidates that we just haven't anticipated so far. And there have been two recent hints that there could be physics beyond the standard model. The first of those hints is relates to the magnetic moment of the muon, which is it's kind of like a massive electron. And another hint has to do with what happens when B mesons decay. So you might have heard of this. There was a lot of press regarding this. There's an experiment that they just completed at Fermilab where they were trying to increase the precision of their measurement of the magnetic moment of the muon. And they were able to show that their measured value disagrees with the theoretical value that's calculated using Feynman diagrams with a significance of about 3.7 sigma. In physics, they want a new result to differ from an expected result by 5 sigma to be considered a valid discrepancy. So this made a lot of press because it made it sound more and more likely that there could be new physics, because this seems to be something that's outside of the standard model. But it turns out that if you take a different approach to using the standard model to calculate this magnetic moment, that you get a value that actually agrees with the experimental value and doesn't agree with the other calculation. And it's well understood what the differences between those two calculation methods is understood. And this lattice-based method is supposed to be more accurate. So it doesn't really seem like this is going to pan out, like there really is any new physics there. However, there was this other example. So with the Large Hadron Collider, they were able to observe a lot of decays of B mesons. And when they made those observations, they noticed that muons seem to be produced a lot less often than electrons in those decays. But muons and electrons, a muon's really more like, it's really like a massive electron. They're supposed to be, as far as the standard model is concerned, they're supposed to be exactly the same with respect to the electroweak force and only differ in terms of their masses. So according to the standard model, the decays of these mesons should produce the same numbers of muons and electrons. Currently, they're upgrading the Large Hadron Collider. And when that upgrade is complete, they're intending to explore this more carefully. Right now, the current result has a significance of 3.1 sigma. So they need to collect more data before they're sure whether this is a real phenomenon or not. So there is some possibility that there might be some physics that we just have never encountered before. Another interesting paper that came out recently was this one where a team of astronomers took a very close look at the rotations of 153 galaxies. And they found evidence for something called the external field effect. The external field effect is a prediction of modified Newtonian dynamics, which is kind of a phenomenological alternative gravity theory. And one thing that's interesting about this is that the external field effect can't be explained using particle dark matter. Basically, what the external field effect is it's an influence that other massive objects in the neighborhood of a given massive object have on dynamics within that object. So this adds more evidence for some kind of alternative theory of gravity, and is evidence against the idea of particle dark matter. Interestingly, it turns out that one of the astronomers, one of the authors of this study, is Professor James Schaumbert from the University of Oregon. He's spoken to us several times in the past. And so it might be fun to check in with him and get the inside story on this paper. Okay, so another result that has to do with the idea of an alternative theory of gravity was this little tidbit that I ran across. So one of the major criticisms of alternative theories of gravity has been that they haven't been able to reproduce the statistical structure that's seen in the cosmic microwave background. And so just a few months ago, a paper came out that provided a new alternative theory of gravity that actually can reproduce the structure, the statistical structure of the cosmic microwave background. So this might not be a deadly criticism of the idea of an alternative theory of gravity after all. And then finally on this topic, there have been some suggestions recently that maybe what we really need is some kind of synthesis of the ideas of particle dark matter and alternative gravity to actually explain all of the phenomenon that we see. So the idea is that you could somehow combine a different theory of gravity with cold dark matter model, and that the transition between where one applies versus the other one is governed by some kind of phase transition. So people have been working on this kind of an idea as well. The last little thing that I wanted to point out that I thought was pretty interesting too, is that it turns out that there's a possibility that there's actually a systematic bias in the data that underlies the idea of dark energy. And that systematic bias might actually negate the entire idea. So it could be that the whole idea of dark energy is just basically a statistical error. So there's a paper about this, and I gave you links to a couple of YouTube videos that are pretty fun descriptions of this idea as well. So that's all I really have in terms of cosmology and astrophysics news. So if you have any questions about any of these things, I would be happy to try to answer them. So you can either just unmute yourself and ask, or you can type in the chat.
So where are you going to post this?
So we're going to collect all the videos from the different sessions in the fair, and they'll be posted on the club website. They'll be linked to the fair. So just like last year, we'll have a bunch of different videos that'll be all posted together, and I think we'll post this with those videos as well.
Mark?
Sure.
So on the lambda CDM versus modified Newtonian dynamics topic, are there any? So essentially, how do these, as I understand these topics, I mean, both these theories are trying to explain existing observations, but do you know if they differ or how they differ in making predictions? I mean, are when it comes to testing, either of them, what do you think is the way, to go about? Essentially, is there a definitive test where you could say which one of these is right, which one is wrong, if they, assuming they were able to, fully, account for existing observations?
Right. So neither one of these approaches actually accounts for everything that's observed. So, for example, one of the pieces of evidence for dark matter is the rotation curves of galaxies. So, like things in the solar system, if you're further away from the sun, you move more slowly in the solar system. So, like Jupiter moves more slowly around the sun than Earth does, for example. But if you look at galaxies as a whole, out past a certain distance from the center of the galaxy, the velocity of everything levels off.
Yeah.
And so one of the pieces of evidence for dark matter is that odd behavior. And it turns out that dark matter doesn't do very well. I'm sorry, particle dark matter doesn't do very well. So lambda CDM doesn't do very well as far as explaining that. But alternative theories of gravity actually do. There are other things, like I pointed out here, the cosmic microwave background has a certain statistical structure. And cold dark particle matter actually does a pretty good job if you tune everything just right in lambda CDM, and it takes particles with certain properties and so forth. If you tune the particle properties just right, then you can explain the statistical structure of the cosmic microwave background pretty well with particle dark matter. But up to the point of this paper, nobody really knew how to do that with alternative theories of gravity. And there are other things too, in terms of not just the statistical structure of the cosmic microwave background, but the statistical structure of distributions of galaxies and other type of matter in the sky and so forth. A lot of those things are things that have been explained pretty well with lambda CDM that can be a little harder to explain with alternative theories of gravity. So there are already quite a few phenomenon that seem to fall under the rubric of this idea of dark matter that are explained well by one approach, but not explained well by the other approach. I can't give you an exhaustive list. I'm sorry, because I didn't think ahead to that question, but there are quite a few where there's a disagreement between those two approaches.
Thank you.
Sure. Anybody else have any questions about any of these funky little things? It's fun to just share them with people.
I had one more on your on the picture of the black holes, the map of the black holes, and
Sure.
so there, what does that intensity? What does it represent? The intensity of these dots. Some of them are bright and big, and some of them are faint. Is that
Right.
like the mass, or
So
I guess it has to be the mass of the black hole, right?
So I guess I think I put it, maybe I didn't even put it on the slide. So LOFAR measures really low frequency radio waves. And so it's the intensity of those radio waves. And what's producing those radio waves is there's matter that's swirling around or falling toward those supermassive black holes. And if some of that matter is charged, then it creates these strong magnetic fields, and the magnetic fields produce these radio waves. So the thing
I guess it would be then proportional to the size of the black hole, maybe?
Maybe, you know, it also just depends on how much matter is in the vicinity
Around,
of the black hole. Yeah.
Do you know if this has the if M87 star is in here in this?
I don't know if it's in this swath of sky that they managed to image.
Okay.
Yeah,
because I see there's this one really big, this big blob.
Right. Yeah. Maybe this one over here. Yeah, it could be. So one of the really cool things, I don't know, I mean, probably other people have seen this too, but if you have a reasonable size scope, you can actually see that gigantic astrophysical jet when you look at M87.
Right,
it's pretty cool. Yeah. You don't need the Hubble Space Telescope to see it. All righty. Well, if nobody else has questions, I think we can go ahead and call it a night. Thanks a lot for joining us.
Thank you very much.
You're welcome. I hope you guys learned a little bit or had some fun, and you know, maybe we'll be able to catch up. I know Victor's posts cosmology related news every month. So if you're interested in that kind of thing, stay tuned for his email. There's always a link in there.
Some of these links are already in the past news items that I've posted.
Yeah, so you know, he scours several different journals to try to find things to put in there. So if you're interested in this kind of thing, check that out.
Were all of you here for the earlier universe thing? I can't really tell.
So several people were.
I got in right towards the end, for sure. Yeah, I'm new, so I didn't know about this, but yeah, this sounds very interesting. I think I should. I'm definitely interested in this kind of stuff.
Well, unfortunately, this is one little part of our club that's been a little bit. It hasn't been as active as other parts of the club while we've been meeting remotely.
I see. Okay.
But the one thing that we have been doing is Victor's has been posting the astrophysics and cosmology news every month, and he scours a bunch of journals too.
When we met in person, I would show videos related to cosmology that are really interesting. And we'll resume that once it's safe to do so.
Yeah, it seems like we're getting there.
Yeah, probably
Well, welcome to the club.
Yeah, thank you, thank you. This is good stuff.
Well, I'm glad you could join us. Thanks, everybody.
Right. See you.
I guess
Bye.
hopefully see you next month.
Goodbye.
Bye.
Take care.